I'm going to go ahead and get us started. Can everyone hear me?
Yes.
Okay.
Yes.
Good afternoon, everyone. It's 3 p.m., so we can go ahead and get started. My name is Max Lewis, and I will be serving as the moderator for this seminar for this semester. Our guest speaker today is Dr. Yalin Wang. Dr. Wang received his bachelor's in engineering degree from Zhang University in Shaanxi, China in 2014, and his PhD from Shanghai Jiaotong University in Shanghai, China in 2018. He is currently a postdoctoral researcher with Shanghai Jiaotong University and a visiting scholar with the University of Arkansas. His research interests include dielectric properties of insulation materials and condition monitoring techniques. Today, he presents insulation design of a high-frequency electrical machine for more electric aircraft propulsion. Dr. Wang, are you with us?
Hello. Hello, everyone.
Hi. I will give you the floor.
Thank you. Let me share my screen. Can you see my screen?
Yes. I can see it.
So the bigger one, right? The title, right?
Mm-hmm.
Okay. Good afternoon, everyone. Thank you for inviting me to give this presentation. My name is Yalin Wang. I was a postdoctoral research with Professor Haran's group. I'm grateful for participating in this research, and today I feel happy to share our results with you. The topic is about insulation design of a high-frequency electrical aircraft machine for more electric aircraft propulsion. I'm sorry. So I would like to divide this topic into 5 sections as shown in the list. First, I will give a brief introduction about the more electric aircraft and the challenges for electrical motors that are used for electrical propulsion. Then I focus on the insulation structure of the high-frequency electrical machine, which is designed for the NASA project. The third part is about how to determine the PD-free criteria for stator windings. We performed the partial discharge experiments and combined these experiments with simulation results to derive the criteria. Lastly, I will introduce the trade-off between the insulation reliability and high specific power requirement. The proposed design is also verified by the experiments. So I know some of you are very familiar with the more electric aircraft, some may not, so let me briefly review the history and the advantages of electric aircraft. Electric aircrafts have a long history. The first manned flight of electrical planes was realized in the 1970s. In the past 5 years, electrical planes have developed rapidly. We can see the solar-assisted electrical planes have appeared and completed a global tour in 2015. Nowadays, the scientific research and the industrialization of commercial airliners and the personal aircraft have been booming. The most prominent advantages of electric aircraft are energy saving, high efficiency, and low vibration levels. However, some challenges are also brought to the motor for electrical propulsion due to its special operating conditions. First, since the aircraft is very sensitive to its weight, the propulsion motor needs to have a relatively high specific power. We can see the roadmap of the specific power development. More than 13 kilowatts per kilogram specific power is required for the future. Besides, the power of the propulsion motor is also large. But in order to increase the specific power, the volume of the motor needs to be reduced, which limits the thermal performance of the motor. So the heat resistance of the motor insulation material also needs to be improved. In addition, when the propulsion motor works in a low pressure environment, which is the cruising altitude of an airplane, the partial discharge is more likely to occur according to Parsons law. We can see in the right picture, which greatly threatens the reliability of the motor insulation. The partial discharge inception voltage, which is called PDIV, PDIV is defined as the voltage for the exact beginning of PD. It decreases with the drop in pressure and also decreases with the increase in temperature. Therefore, the problem of partial discharge is the most serious challenge that may be encountered in the motor's insulation. So the background of this study comes from a NASA project. One megamode 1 megawatt high-frequency permanent magnet synchronous machine was proposed by our team to achieve a high specific power to enable the more electric aircraft propulsion. The PMSM adopts the hypo, high frequency, and air gap formed windings to enable an air core topology to achieve the PD-free and thus high specific power targets simultaneously. We optimize the structure of the stator insulation by considering the PD inception criteria and the effect of insulation size on specific power. So the structure of the winding is shown in the bottom right figure. The type 8 lead wire with a rectangular shape formed by 15 bonders was chosen to reduce the AC losses. The lead wire is wrapped in H thermoclass Nomex tape, and each bonder encases 44 coupled strands with the thermoclass H polyimide insulation. Each winding includes 3 overlapping lead wires separated by glass fiber. So ceramic filled epoxy resin is applied between the 3 terms and covers the surface of them to provide structural integrity, enhance insulation, and also improve the thermal conductivity of the winding. So the insulation properties of the lead wire are shown in table 2. As stated previously, PD is the most severe threat to the winding insulation. In this study, we experimentally investigate the influence of air pressure and the temperature on the PDIV of the full-moon winding to derive the criteria for the PD-free design. A PD test bench is built as shown in the figure below. The windings are put in the vacuum chamber, a high-frequency current transformer, HFCT, with a frequency range of 10 kHz to 400 MHz surrounds the ground wire to monitor the PD signal, and the PD signals are recorded by the oscilloscope. Before testing the samples, the measuring system was calibrated with a pulse generator to have 10 picocoulomb resolution. We can see the measured PDIV values at various air pressure from 1 to 0.2 atmosphere, and the temperatures from 30 to 210 degrees C. Each full-moon winding was stressed 10 times at different positions at each temperature and pressure by a ramping voltage to obtain the statistical results. When the winding are under the cruising altitude and the rated temperature, which is 0.2 ATM and 180 degrees C, the PDIV is around 55% of that at a normal condition. So we can see the PD situation will be more severe when we put them in the low pressure. Now we obtain the PDIV values with respect to temperature and the pressure, but how to correlate the experimental results with local electrical field values that can be obtained from simulation. Then the PD-free criterion is proposed. The key is to correlate the PD inception field with experimental results. We can see the 3 equations. First, the normalization is performed to calculate the effect of pressure and the temperature on PDIV. Then the inception field at a low pressure and a high temperature is equal to the product of normalized PDIV and the PD inception field at the normal condition, which is widely acknowledged as 3 kilovolts per millimeter. Hello, can you hear me?
I can hear you. Yep.
Seems like I got connection issues.
Oh,
Okay, so I just stopped, right? So can we continue?
yes, you sound good now.
So which slide? Which slide I stopped? This one?
One more.
Okay. So
Go back.
okay. Oh, this one. So we decided to use the FEM simulation. A three-dimensional model of the proposed stator is built to simulate the electric field and the temperature distribution in a winding. So the W and H denote the width and the height of the one single winding, and they are the key variables that need to be determined to achieve a PD-free requirement. And the properties of the material used in the simulation is presented in table 3. So we just use two neighboring windings because it is enough to, we don't need to generate the whole model. So based on the baseline design, the consideration of the machine's performance, the manufacturing capability, so consider all of these. The W is changed from 7 to 9 millimeter, and the H is changed from 6 to 9 millimeter. The simulation results show the maximum electric field is located at the triple point in the end winding area, as shown in the bottom left figure, which is widely acknowledged. However, the maximum local electric field during the whole time will appear either at the moment of maximum face-to-face voltage or at the moment of line voltage, which corresponds to the position at a face-to-face ground, face-to-ground insulation, or at the face-to-face insulation. So we can see a crossover point, as shown in the middle figure, beyond which the face-to-face maximum field is higher than the face-to-ground, and below which the face-to-face is lower than that of face-to-ground. Therefore, the overall maximum field should be picked to make sure no PD happens at any moment. The three-order polynomial equation is used to fit the maximum electric field with respect to W and H. So we can see the fitting curve agree with the data. However, the simulation above cannot reflect the real situation because the manufacturing errors and the insulation degradations may introduce the voids and the delamination, which will distort the local electrical field. So 4 sets of simulation are analyzed. We consider the size, the position, and the amount of the voids and the air gap introduced due to delamination. We can see the introduced defects generally distort the local electrical field, and the smaller the void, the more distorted the local electrical field. And the local field is even more distorted if the void is located in the middle. Regarding the air gap introduced by delamination, the smaller the thickness of the air gap, the more distorted the local electrical field. So based on the simulation results, we introduce a scaling factor K. It is added to modify the PD-free criterion as shown in the left equation. So in terms of the temperature simulation, we can see the end winding area is the hottest because it is far away from the heat sink. And also it is found the maximum temperature increases with age because the thermal resistance increases with the thickness of insulation between the lead wire and the iron yoke. But the maximum temperature decreases with the increase of W, which is because the volume of heat sink increases and the more heat will be dissipated. So we use one order polynomial relation to fit the temperature. We can see it also agrees with the data. Now we have built a relation among the insulation sites, the electrical field, and the temperature distribution. As stated previously, the target is to achieve high specific power and the PD-free simultaneously. The size of the insulation not only affects the local electrical field, but also the size of the motor, then influence the specific power. In order to balance this issue between the high specific power and the PD-free requirement, a multi-objective genetic algorithm was utilized to obtain the optimal Pareto Front for each air pressure. The constraints are the maximum electric field should be lower than the PD inception field, and the maximum temperature should be lower than the rated temperature of the insulating material to ensure long-time reliability. And the objective functions are maximizing the electric field margin and the specific power, as well as minimizing the temperature. The Pareto Front is obtained from the multi-objective genetic algorithm. It can be observed that the increase in electric field margin will lead to an increase in maximum temperature, which is unfavorable for reliable insulation design. And the maximum temperature increases, but the specific power decreases with the decrease of air pressure at the same electrical field margin, which means the drop of air pressure will harm the insulation and harm the performance of the motor. The blue dotted line and the arrow in the middle figure show the acceptable solutions for PD-free design by considering the actual margin. The margin is originated from the introduced defects. So for the first scenario as 0.2 atmosphere, the acceptable solutions can achieve the maximum 13.8 kilowatt per kilogram specific power and keep the maximum temperature around 155 degrees C. So for the final design, we just need to consider the worst scenario, which is the 0.2 ATM. The parameters of the final PD-free design as shown in table 4, 5 windings with the adapted insulation thickness have been manufactured and tested in the PD test bench. The PDIV of 5 samples were measured for 10 times, each at 0.2 atmosphere and 180 degrees C to obtain the statistical distribution. And this data are verified, are used to verify the PD-free design. The PDIV results are shown in the figure and analyzed by the 2-parameter Weber distribution. It is found that the PDIV of these windings has 99% probability to be higher than 1000 volts, which is higher than the rated voltage. So now the proposed design is verified by experiments. Finally, we can draw the conclusion that the insulation design of stator winding is proposed regarding the requirement of PD-free and high specific power. The experimental results and the simulation results are combined to derive the PD-free criterion. And the optimization and the final design is verified through PDIV experiment. We hope the proposed design procedure can provide useful references for electrical machine insulation design to enable the more electric aircraft propulsion. So thank you for listening. And any questions?
It doesn't seem like there's any questions. So thank you, Dr. Wang, for presenting. We all appreciate that.
Thank you.
And I think, is there anything else, Ms. Smith?
Yeah, I think we can probably talk about Becky if there's no question to Dr. Wang.